Hi, this is Chris Armstrong from RIGOL Technologies. Today we're going to be talking about serial communication on your IoT device. We're going to make measurements of decoding, noise, and latency, and look at how RIGOL instruments can help you improve these measurements and debug your IoT devices. All right, here we are with our first serial communication setup, looking at an SPI bus between two IoT development boards. So when you're developing your IoT product, working on an SPI bus, one of the first things you want to be able to do as you debug your code is monitor that bus, both physically and for the code it's being sent. So here we've hooked up our oscilloscope, looking at the chip select, clock, and data lines. We can also trigger on individual data elements, as we're doing here, triggering on the first ASCII code that's being sent across. We can also decode it on screen, so we can see that that's an ASCII R being sent as the first piece of that packet, and as your code changes and your packets being sent or changing, you can see how those are affected. You can also record a number of these as packets, as different transfers. Here we're recording a set of them using record mode. We can go ahead and look at that then. We can go deeper and analyze it. So here we can set a pass-fail mask around our data, so we want to see how much that data is changing, how much is fluctuating, and what other packets are being sent. So here we see that they all are basically identical in this setup, but you could test for other packets or other data elements as well. So there are a couple techniques we just used to measure decoding of your serial data on your SPI bus. One of the tools we use to do that is the serial decode option on RIGOL oscilloscopes. Our 4000 series has a number of serial decode options, but the 1000Z and 2000 series instruments decode serial data as well. Today there's a bundle pack for the 2000 and 4000 series that allows you to get all the decoding options at one low price. Now that we've completed our look at decoding techniques, let's look at noise and crosstalk and how that might affect our signals on our IoT device. Now we're back with our oscilloscope looking at our IoT SPI bus. We've zoomed in on the signal a little here so we can look at some different characteristics of these signals. You can see on the chip select there's a little bit of noise here running along as the crosstalk over from the clock. There's a couple things we can do to make it look a little better on the oscilloscope. One of the things we could use is a high resolution mode, which will reduce the noise a little bit. We could also use our bandwidth limits on our analog channels. That improves it significantly more. The other thing you can do with an MSO that's worth doing is to look at this on the logic channels. So we've also tapped the same lines with the logic channels, and you can see them up here at the top of the screen. We can also do a decode on those channels as well. So one of the things you want to look at as you're analyzing your setup for your IoT device is to make sure that that noise and the bandwidth on those signals isn't affecting their actual decoding in digital sense. So you can look at it digitally with the logic analyzer channels, but also make sure to look at it with the analog channels so you can see any noise or grounding or other issues that might be causing you trouble as you decode your signals. We just demonstrated a couple of techniques for measuring the SPI bus on your IoT device. We used the analog and digital channels of a 4000 series RIGOL oscilloscope. Now let's look at some timing measurements we can make on the same SPI signals. The last thing we want to look at today on your SPI bus is some timing and latency issues. How your code is implemented has a big effect on latency and timing, and how quickly the serial data can be acknowledged. So we've done a couple things. First, we've added another probe here. We're going to turn this channel on, and this is really tied to an acknowledge bit on the slave. So if we zoom in time here, we can see the acknowledge bit happens a fixed time after the transmission. So really, whenever the SPI bus is communicated, it's received in about the same amount of time. We can use a cursor to quickly look at that toggle. So from the time the chip select first goes down to when the acknowledge toggle occurs, in this case is about 81, just about 80 microseconds. So that's a measurement we can make. We can optimize our code around that to help get the fastest response time we need, based on what we're trying to do with our IoT device and how quickly we need to respond to actions over the bus. In summary, when debugging serial communication on your SPI bus for your IoT device, you want to look at important things like the connections, noise, latency. You want to do decoding, as well as look at the analog signals themselves. All these techniques help you to improve both the efficiency and optimize your peripheral implementation for your IoT device. Today we used 4000 series oscilloscope, mixed signal oscilloscope, and the serial decode as part of the bundle pack. The products we used together would cost about $4,605. Thanks for listening. If you have any questions, you can always reach us at www.rigolna.com.